Hello, wonderful people, and welcome to the Diet NPO Podcast. My name is Zach Caseberg, MSRDN, and I will be your host. I hope you're feeling energized for another good week, and I know I've really been recovering from my past weekend. You always know when you're pushing it too far, whether that's at work, it's at workouts, it's you studying for the RD exam, whatever it is, you know when you feel like you're pushing it too far. And knowing yourself and knowing your limits can be really helpful for some of my students to know what is actually a realistic goal that they can get to, no matter what those goals are, no matter what it might be. I had a recent goal that I was happy enough to achieve, if only barely. I was always an athlete when I was a kid in high school, but I was never good enough to take it on to a collegiate level. So that made it difficult to want to stay motivated to work out. So that's kind of how I fell into nutrition in the kinesiology fields. Now, while I wasn't good enough to do collegiate athletics, I still had some great experiences working with athletes and continuing to work out myself a lot more through my 20s. One thing I always struggled at, though, always, was aerobic workouts, like running primarily. I swam as a kid, I bike all the time. I just needed to learn how to run efficiently so I could do these races. And I did that so that I could participate in these triathlete races that I do about once a year, these short sprint triathlons, which I had this past weekend. And yeah, your body feels it after. But it's easy, and it's the best excuse to relax for the rest of the weekend once you've done a large physical task like that. That being said, it reminded me of all the value that sports nutrition provides to competing and non-competing athletes. And I also know that sports nutrition has its ability to make its way onto the RD exam. So I thought, what a better concept to talk through with you today. Now, it's generally easier to learn something when you're intrinsically motivated to do so. And I think for some of us, we love to hear about sports nutrition because we love working out. For some of us, we may not be as passionate, and for others, it might just vary. I'm going to try and give you some relevant information from my recent event to really help you give some ideas and connect the dots of sports nutrition. We'll discuss a bit about the aerobic versus the anaerobic metabolism pathways and see how it fits into an athlete's exercise in their racing routine. We're also going to talk a bit about respiratory quotient as well as VO2 max. Now, we all know the basics, right? Human bodies need energy continuously to perform most of its functions. We always know that. As someone who exercises more, moves more, has more stress, or even more catabolic disease, the body is going to will need to be provided with additional energy. We've discussed the difference between aerobic and anaerobic metabolism before in past podcasts, and we know that this is an essential part of understanding sports nutrition because it's going to dictate what type of energy system that you'll be using during exercise. But a reminder, aerobic metabolism is when I'm working out and I can breathe just fine and have plenty of oxygen. Whereas anaerobic metabolism is where I'm going all out and we don't have oxygen in that case. What sport would you say focuses the most on being fast right out, fastest at the start? Maybe you'd say a sprinter out of the blocks or a football player out of the line. What we know is that when we're doing this short movement, say 5 to 15 seconds or so, this is known as this immediate energy system, which is using ATP from an ATP pool that's just hanging out in your cells, as well as the Creatine-Phosphate Pathway. This pathway helps to produce a lot more ATP immediately, and it's actually the fastest rate of ATP production, but it only lasts a short period of time. We're going to need to rely on some other energy systems if we want to do any workouts longer than 15 seconds. So let's say we're doing a run for 1 to 3 minutes, but it's an all-out race. Maybe it's that last 3 minutes of a run that you're doing and you're just trying to finish it off, get home, and get your coffee like I usually am. At this point, we're going to try to rely on our anaerobic pathways to produce ATP. The first pathway being anaerobic glycolysis. You remember that guy, right? When we're yielding energy out of glucose to produce ATP. Remember, as we move a molecule through glycolysis, we actually yield 2 net ATP. And that's because when we go through glycolysis, we produce a whole 4 gross ATP, but it actually takes 2 ATP to spend to get this process going. So that's why we say it's 2 net ATP. Now that's nice, but that's not a lot of ATP for you and me. So we're going to have to use this pyruvate that we get through glycolysis to send it somewhere else. Normally, under aerobic conditions, we would just take that pyruvate and shuttle it on to the Krebs cycle, right? We're not able to do this though. We can't get into the mitochondria without oxygen. So what are we going to do with this darn pyruvate? What are you going to do with it if you know what pyruvate is going to be converted to? Say it out loud with me. It's going to be converted to lactate through the Cori cycle or the lactic acid cycle. Lactic acid, aka lactate, can be then converted back into glucose through gluconeogenesis, and we're starting this process all over again to yield that ATP in these anaerobic pathways. Note that you've probably heard of lactic acid building up in your muscles and causing you to be sore. This is true. Exercise, and as muscle increases its demand, the lactic acid can build up. It can cause muscle pain and even fatigue. This proves that anaerobic pathway might not be the most infinite option. Aerobically, though, we have an almost unlimited ability to make ATP. It's just at a slower rate. These types of activities are going to be when we're doing long duration activities, such as an event, my triathlon this past weekend, which was just under 90 minutes, not my favorite time. We're probably relying heavily on a lot of those aerobic pathways when we're doing these long events. We may have many different pathways to keep straight here, so stick with me. Let's start with aerobic glycolysis. Remember, we produce 2 net ATP right off the bat through glycolysis. But now we get to take that pyruvate and send it into the Krebs cycle. Once that Krebs cycle takes the pyruvate, makes it into acetyl CoA, we send acetyl CoA through that circle, and we are stripping off hydrogen molecules to produce certain intermediates. Those intermediates are known as NADH and FADH. Know these as being the 2 major end products that come out of the Krebs cycle. These 2 are like a check that we're going to take to the bank to cash out. We're going to take this NADH and FADH checks to the electron transport chain, which has ATP synthase, and it can process these checks to make them into a giant amount of ATP. And that's just carbohydrates right there that we talked about to go through glycolysis, Krebs, and then the electron transport chain. We know fats are also a great source of energy for ATP, and especially in those aerobic conditions. Fats are first being run through beta oxidation, a process that produces NADH and FADH, as well as some acetyl CoA. Then we know where we're going to take these byproducts. The acetyl CoA will go to the Krebs cycle to make more checks, more NADH, more FADH, and all of these are going to come together to go through the electron transport chain, which is your bank, and we're going to cash out those checks. Now to the proteins. The proteins contain nitrogen components that can be metabolized for energy, and through transamination, through deamination, we can make our amino acids into various types of inputs that are necessary for the glycolysis and the TCA cycle. So it's helping to keep this process going too. So as you see, carbs are directing everything through the TCA. Same with fats, producing acetyl CoA, and funneling things through the TCA to use that electron transport chain. Proteins are also providing a certain other inputs along the way to help with energy metabolism. So these are exciting to get these used. Now, it's all about how can we use these pathways to increase our ability to work out longer and work out harder. Well, as you train more, your cells, your muscle fibers, they adapt, and your ability to use oxygen actually changes. Make note of a term you've probably seen on an Apple Watch before or any type of sport watch. It's called your VO2 max, which is your maximal rate of oxygen consumption that is attainable during exercise. I think of it as how high is the ceiling at which I can stay in aerobic metabolism. It's the max of that. If I complete more aerobic activities and if I train more, my VO2 max is going to increase and I'll get in better shape and I'll be able to use my aerobic metabolism pathways a lot more at that higher ceiling. That's why it's so good from a biochem standpoint. You've already learned about these different pathways, and now if I work out more and I can use more oxygen, I have an infinite number of pathways that I can use to produce energy. Okay? Now you've learned about VO2 max, you've stuck around to kind of see what that is. Maybe let's apply it to a little bit of our own workouts and maybe to a practice question to make sure that we really understand how to go through this here. Let's talk about a practice question. If an athlete is training and develops a higher VO2 max, they would be relying more on which of the following processes? An athlete is training and develops a higher VO2 max, they would be relying more on which of the following processes? Would it be A, anaerobic glycolysis, B, lactic acid cycle, C, the creatine-phosphate pathway, or D, aerobic glycolysis? So I'm going to eliminate the ones that I think are bad fits. So as they develop a higher VO2 max, they're going to work more on this one. I don't think it's going to be A, because anaerobic glycolysis, if we're relying more on anaerobic glycolysis, then we're relying more on this pathway that doesn't use oxygen. That doesn't seem to fit well if my VO2 max is going up. So that's out for me. B, the lactic acid cycle. We know this is also being an anaerobic pathway. It's where we're going to take that pyruvate and make it into lactate or lactic acid so that it can then be made into gluconeogenesis. I don't think that's going to be our pathway for the VO2 max going up. C, the creatine-phosphate pathway, which is really good for 5 to 15 seconds at a time. I don't think this is going to be touched too much by that increase in VO2 max. I would feel it's D, aerobic glycolysis, because I think as my VO2 max climbs up, I'm going to be able to then use more oxygen and have better use of aerobic glycolysis as a result of this. So that's the really exciting part of that. For this athlete, now they have a higher ability to use oxygen for energy. That switch from aerobic to anaerobic is now a higher ceiling, and the athlete has a lot better use of their aerobic pathways. For the exam, we need to be familiar with another concept of respiratory exchange that is called your respiratory quotient. The respiratory quotient is a formula or a ratio that is saying how much carbon dioxide do I produce for every molecule consumed. And this will be for which macronutrient that I'm using for fuel at that point. So again, it's the how much CO2 is produced divided by how much oxygen is consumed. So it's represented on a scale based on the macronutrients that the body is using as fuel, where 1.0 represents carbohydrates, because carbs produce one CO2 molecule for every one oxygen consumed. So I'm producing a lot more CO2 than I might with other macronutrients from carbohydrates, and that's no good. Protein is closer to about 0.8, as it produces a little bit less carbon dioxide for every one molecule consumed when it's used for energy there. And 0.7 is our best fuel, which is our fats. Fats will have an RQ of 0.7, which means it's going to produce 0.7 molecules of CO2 for every one molecule of oxygen. which is great because that makes it just more infinite for use for energy. Now let's give you a few more questions to dive into before we have our What's Eating You segment today. Under anaerobic conditions, pyruvates can be converted into blank through the Cori cycle and can then be converted into blank through gluconeogenesis. Under anaerobic conditions, pyruvate can be converted into blank through the Cori cycle and can be converted into blank through gluconeogenesis. Let's check out our answers here. For A, lactate acetyl CoA. Under anaerobic conditions, pyruvate can be converted into lactate through the Cori cycle. That's true, and can then be converted into acetyl CoA through gluconeogenesis. That is false. Acetyl CoA is not going to be converted. Lactic acid is not going to be converted to acetyl CoA through gluconeogenesis. Doesn't make sense. How about B? Pyruvate can be converted into acetyl CoA through the Cori cycle. No. And can then be converted into glucose through gluconeogenesis. So no, we're not going to take acetyl CoA. Pyruvate's not going to be made into acetyl CoA under anaerobic conditions. So B is out. C is pyruvate can be converted into lactate through the Cori cycle. Okay. It can then be converted to blank glucose through gluconeogenesis. I like that answer and I like that one really well. For D, pyruvate can be converted into acetyl CoA through the Cori cycle. Nope. And can then be converted to NADH through gluconeogenesis. That is not it. So C is my best fit. Pyruvate will be made into lactate through the Cori cycle, and then it's going to be made into glucose through gluconeogenesis. The pathway of aerobic metabolism that is producing the most amount of ATP through NADH and FADH intermediates is known as what? The pathway of aerobic metabolism that produces the most amount of ATP through NADH and FADH will be what? Will it be Krebs, citric acid cycle, aerobic glycolysis, or the electron transport chain? All right, so I'm going to go ahead and eliminate the citric acid cycle. I know this is an anaerobic pathway, and we're talking about aerobic. So I know it's not B. I don't think it's C either, because aerobic glycolysis does not produce the most amount of ATP through NADH and FADH intermediates. I don't think it's that, nor the Krebs. I think my best answer is the pathway of aerobic metabolism that produces the most amount of ATP through NADH and FADH intermediates, be known as the electron transport chain. Today on the What's Eating You segment, I've got to celebrate a win here. One thing we generally try to do as my job as a food service RD is focus on whole-based recipes and products. We want it, our students want it, we can control the nutritionals more. It's great. And one recipe we wanted to make was a cauliflower taco meat, a vegan item that is made to represent taco meat for a bowl, a taco, a burrito, you name it. I adapted this recipe from savortheflavor.com as I needed to make it a bit more allergy friendly for our customers. In a food processor, I combined cauliflower, sunflower seeds, pumpkin seeds, sun-dried tomatoes, oil, mushrooms, onion, and garlic. Now, serving this as a base for your taco meat, I pulsed these ingredients kind of slowly in a food processor, but it was tricky. So a quick tip is maybe process those cauliflower florets separately so you can make them into the crumble consistency you want. Because if you add everything together, you're probably just going to pulse all the ingredients and end up with this unattractive paste. So you can kind of do your broccoli florets separately and then use all your other ingredients as their own kind of ingredient mix after that. The perfect combo that we added for a seasoning of mixing all these ingredients was chili powder, cumin, salt, paprika, cayenne, water, and lime juice. Once we mixed all this mixture very thoroughly, we spread it out onto a full sheet tray, one of which I put parchment paper and one I did not. And let me say, use the parchment paper. It's going to make your life a lot easier and you're going to scrape a lot less. I can promise you that. We put it in a hot oven 10 to 11 minutes at a temperature of 400 degrees Fahrenheit, and you may be surprised about what comes out. You get this spread that's dehydrated, and once you remove it from the parchment paper, it breaks up really easily into this excellent vegan entree that can be mixed into all kinds of items for your Taco Tuesdays. But that wraps it up for you nutrition enthusiasts. I hope you wanted to learn more today. Don't forget to rate, review, subscribe. Check me out all over on Threads, on Instagram, on YouTube at Zach_snacks. Please rate and review to help the show as much as we can. We're posting some questions occasionally on Threads, so take a look at those for you to get more practice. Have a good one, and as always, to my favorite RDs to be, happy studying to you. I'll see you later.